Hello, in this lesson we're going to be speaking about gravitational force, and we're going to show that it's a type of central force. So gravitational force, not just on Earth but in general, is a force which looks like this. So it's equal to negative g, which is some kind of constant which is written over here, multiplied by m times m, so the mass of two bodies, divided by r squared, and it's of course going in the radial direction. Okay, so it's the attractive force between any two bodies which have a mass. Now, a lot of the times we're going to be working with one mass which has a huge mass, and another one which is very, very small. Okay, so that's why they're represented by a capital M and a small m. So, for example, when working with Earth, so we can see Earth has a huge mass, and then the person standing on Earth has a very tiny mass. Okay, and then this is the equation to work out the force between the two. So between every two bodies, there's this type of force. Okay, so if another person was standing over here, for instance, so there will still be this gravitational force between these two people, or these two small masses, but because the force is going to be so tiny, then it's something that is negligible and we don't really take that into consideration. Now here we have our r squared, okay, so our r represents the distance between the two masses, and the distance is measured from the center of mass. So for instance, from Earth, our center of mass is somewhere in the center of the sphere, okay, so our r is going to go from the center of the sphere until the center of mass of the human. Okay, so this is our r. And of course we have our r hat over here to show that our force is acting in the radial direction. And we can see that there's a negative sign over here, meaning that our origin is located over here, okay, at the center of the Earth, and that our human is being pulled towards the center of the Earth. Okay, so I can rub that out and draw it like this. Now we can see that our gravitational force is a central force because we can see that all of this over here is some kind of function with respect to r, so that's our Fr, and then it's acting in the radial direction. So from the previous lesson we can see that that's the format for central force. Okay, so we now know that this is a central force because it's in this format, and therefore if this is a central force, then we know that we're going to have conservation of energy and of angular momentum. Okay, so if we have conservation of energy and of angular momentum, that means that our energy is equal to some kind of constant, and our angular momentum is equal to another constant. Okay, so we know that our gravitational force is denoted by mg. Okay, and it's something that's constant, and suddenly we see over here that our gravitational force is dependent on the distance, okay, our r squared. So let's take a look at how we connect this equation to our mg, how we got this constant from it. So usually when we're working with our gravitational force, we're working with it close to Earth. Okay, so that means that our delta H is significantly smaller than the radius of Earth. Okay, so the radius of Earth, let's write our RE, is equal to something like 6,400 kilometers. Okay, so that's around about the radius of Earth. Okay, so when we're working out the gravitational force of some building, okay, where it's delta H of the building is equal to, let's say, 20 meters, so we can see that 20 meters is significantly smaller than 6,400 kilometers. Okay, so we're doing this kind of approximation.